Hey guys, today we're going to learn how to solve differential equations. Now, a differential equation is any equation that basically involves derivatives. When we're solving a differential equation, what we are given is the equation of the derivative, and we have to find the exact function that led to that derivative. So there are three terms that you'll need to know. One is the initial condition, and this is a function value that could be used to solve for the constant of integration, which we've done questions like this before in the past. Two is a general solution. That is exactly when you integrate and you have your solution that involves the constant of integration, meaning c. The particular solution is once you solve for c and you plug it back into your function, and then that would be the solution that you are trying to find. So below we have an example of a differential equation. We have dy dx is equal to 6x squared plus 6x plus 2, and we are given the initial condition, which is f of -1 is equal to 2. So when we are solving a differential equation, what this means is we have to integrate because we're trying to find the function, and what we're given, as you can see, dy dx, is the derivative. But when we're integrating, both sides of the equation have to be, or rather one side has to be in terms of y, and the other side has to be in terms of x. So dy over dx, we would have to separate it, and that typically in an FRQ is one point within itself. So we already see that on this side of the equation is all x's, so we want the dx to be on that side. So what we're going to do is we're going to multiply dx over to the other side. And what we end up with is dy is equal to 6x squared plus 6x plus 2 dx. And now we integrate both sides. See, when we're integrating, we never really see integrating dy dx. We see just one variable, always closing the end of that integral. So either dx or dy or dt, etc., which is why we separate the dy dx. When we integrate dy is the derivative of y, hence dy. So when you integrate, that's just going to be y is going to equal to, and now we integrate all of this. Now this would be 6x to the third over 3 plus 6x squared over 2 plus 2x plus c. We can simplify this. This is y equals 2x to the third plus 3x squared plus 2x plus c. This is the general solution. This is the one that involves c. But what we need to find is the particular solution, and that's where the initial condition comes in. We're going to plug in x is equal to -1 and y is equal to 2 so we can solve for c. So 2 is equal to 2 times -1 to the third plus 3 times -1 squared plus 2 times -1 plus c. We work this out. 2 is equal to -1 to the third is -1 times 2 is -2. -1 squared is +1 times 3 is a +3. 2 times -1 is -2 plus c. So continuing on, we have 2 is equal to -2 plus 3 is 1, minus 2 is -1 plus c. So now we just add the 1 over to the other side, and we get that c is equal to 3. Now that we have c, we can write out our particular condition. So we come back here to our, particular solution, sorry. We come back to our general solution and we plug in c. So my final answer would be y equals 2x to the third plus 3x squared plus 2x plus 3. And this would be my particular solution and my final answer. Let's try a couple more examples. We have here dy dx is equal to 1 plus 12x to the 3 over 2 divided by 2 square root of x. So we see here on this side, this is already all in terms of x. Now you have to kind of think ahead, right? Well, our goal here is to integrate. This is going to be very difficult to integrate. But luckily for us, what we are dividing by here is a monomial. So that means that I can take everything in the numerator and divide it by this monomial. Or if it makes it easier, you can bring this up and then the square root of x up and then distribute. Let's see what works out best. I'm going to do here is I'm going to separate this. So this is dy dx is equal to 1 over 2x to the negative 1/2 plus, so what I did here is 1 divided by 2, so 1/2, and then I brought the square root of x up, which is x to the negative 1/2. Now I'm going to divide these. 12 divided by 2 is 6. Keeping in mind that this is x to the 1/2, so we would subtract these exponents. 3 over 2 minus 1/2 is 2 over 2, so just 1. So this would be x to the first power, which is just 6x. So now that this is a little bit easier to work with, I'm going to multiply dx over to the other side so we can integrate. So I have dy is equal to 1/2 x to the negative 1/2 plus 6x dx. And now we integrate. So the integral of dy is y is equal to 1/2 x. I have to add 1 to the exponent, so I'm adding 2 over 2, which would give me 1/2. And then divide by the new exponent, which is multiplying by the reciprocal, which is 2, plus 6x squared over 2 plus c. Let's simplify this a little bit so we can work with this a little easier. This 1/2 and the 2 will cancel. And x to the 1/2, that's just the square root of x plus 3x squared plus c. So again, this is my general solution. I am now going to plug in my particular condition, my initial condition, sorry, in order to solve for c. So f of 4 is equal to 52. That means that y is 52. And I'm going to plug in 4 for x. So we have 52 is equal to 2 plus, now 4 squared is 16 times 3 is 48 plus c. 2 plus 48 is 50. So we get 52 is equal to 50 plus c. Subtract the 50. And we get that c is equal to 2. So now I'm ready to write my final answer, which is my particular solution, which is y is equal to the square root of x plus 3x squared plus 2. And this will be my final answer. Now over here we have dy dx is equal to x squared plus 2x divided by 2y. Now we want the y's to be on the same side and the dx's on the same side, and the x's. So what I'm going to do here is I'm going to multiply 2y over to the other side. So what we have is 2y dy dx is equal to x squared plus 2x. And now I'm going to multiply the dx over to the other side. So that way what we see here is we have separated our variables. So we have only y's and dy's on the left and the x's and dx's on the right. So 2y dy is equal to x squared plus 2x dx. And now we're ready to integrate. The integral of 2y is 2y squared over 2 is equal to x to the third over 3 plus 2x squared over 2 plus c. We can simplify this. We get y squared, since these 2's cancel, is equal to 1/3 x cubed, or x cubed over 3, however you prefer to write it, plus x squared plus c. Now I have here as a tip. This one didn't really matter because we were able to solve for y pretty easily. But to solve for c, it's sometimes easier to solve for c immediately after you integrate before you solve for y. Because our end goal here is to have our equation only in terms, like just y equals, etc. So we want an explicit equation for y. So if we do that, that kind of reduces the difficulty for solving for c. So I'm going to right now plug in my initial condition. Now this isn't to say that you can't do this at the end, but just if you want to reduce difficulty, you can do that now. So I'm going to plug in the 1. So for the y, so that's 1 squared is equal to 1/3 0 cubed plus 0 squared plus c. So this makes it a lot easier because what I have here is 1 is equal to c, since this is all 0. So now I have here my general solution. Y squared is equal to 1/3 x to the third plus x squared plus 1. Now we want to solve for y, so we would have to square root both sides. So y is equal to plus or minus the square root of 1/3 x to the third plus x squared plus 1. Now remember, it's important to note that any time you square root, your answer is always plus or minus. However, there can only be one particular solution, and that depends on the initial condition. We see here that f of 0 is equal to positive 1, not negative 1. So that means that my particular solution has to be the positive version of this square root. So my actual answer is y equals the positive square root of 1/3 x to the third plus x squared plus 1. Now, let's look at another question. And I put here just because we did this before, but when we work this out, when you're solving a differential equation where the solution involves a radical or a natural log, you must take note of the sign and the value of the initial condition. And you'll see now what I mean by that. So let's start separating our variables. So a differential equation is sometimes called a separable differential equation simply because you can separate those variables, which is exactly what we do here. We see that we want to get the y's on one side and the x's on the other side. So if you look at your equation here, you see how the y's here are diagonally across, and so are the x's. So what you can do, which is what we did before without really saying so, is cross multiply. So dy times y is y dy is equal to x plus 2 dx. And now we're going to integrate. The integral of y would be y squared over 2 is equal to x squared over 2 plus 2x plus c. So again, this is my general solution. I just integrated. I'm going to plug in my initial condition to solve for c. And again, I do this now because it makes it easier in the long run when you're trying to, like if you try to solve for c later after you solve for y, you're going to have square roots, and it can be a little bit more difficult to figure out if c is positive or negative. So it's just easier to do it now. So we plug in x is equal to 1 and y is equal to -3. So -3 squared over 2 is equal to 1 squared, which is just 1, over 2, plus 2 times 1, which is 2, plus c. Now this is 9 over 2 is equal to 1/2 plus 2 plus c. Now we want to solve for c, we could put this over 2, so that way everything has a common denominator. So this is going to be 9 over 2 is equal to 1/2 plus, this is 4 over 2, so 1 plus 4 is 5 over 2 plus c. Subtract the 5 over 2, and we get that c is equal to 4 over 2, which is just 2. So now we're going to plug this into my general solution. If it's helpful, sometimes when you integrate, put maybe like a star by it so you know which one, you don't have to look for your general solution as you work, because sometimes these questions can get pretty long. So we're going to plug in the 2 for c. So y squared over 2 is equal to x squared over 2 plus 2x plus 2. Keeping in mind that we're trying to solve for y here. So I'm going to multiply 2 to both sides, meaning I have to multiply the entire right side by 2. So y squared is going to equal to x squared plus 4x plus 4. And then we square root. So y is equal to plus or minus the square root of x squared plus 4x plus 4. Again, look at your initial condition. It is negative. So that means that my particular solution must be the negative version of the radical. So my actual final answer is y equals negative square root of x squared plus 4x plus 4. Let's look at another example. We have here dy dx is equal to x to the 4th times y minus 2. So we want to get the y's over to the left, the x's over to the right. So what I can do here is I'm going to multiply the dx over. So we get dy is equal to x to the 4th times y minus 2 times dx. Now we can divide this y minus 2. And if you prefer, what we have here is dy over y minus 2, or you can write this as 1 over y minus 2 dy, either way is fine, is equal to x to the 4th dx. Now we're ready to integrate. Now if you look here on the left side with the y's, 1 over y minus 2. The derivative of the denominator, y minus 2, would just be 1 or dy, which is what's in the numerator. So this must mean that this is ln. So this is the ln of y minus 2 is equal to x to the 5th over 5 plus c. So this is my general solution. Let's go ahead and plug in this initial condition. So f of 0 is equal to 0. That means that the ln of 0 minus 2, or negative 2, and remember, whenever we integrate and we get ln, we put this in absolute value, because as I've mentioned before, ln is only defined for all positive numbers, not negative numbers. So that way this absolute value takes care of that negative. Is equal to 0 to the 5th is just 0, so c. So that means that c is equal to the ln of positive 2. So now we can plug this in to our general solution here. So the ln of y minus 2 is equal to x to the 5th over 5 plus the ln of 2. Now, as I've mentioned, we want to solve for y. So what we have to do is, to get rid of this ln, we have to raise everything to the e. So I'm going to apply e here as well as e here. So this will cancel, and we have the absolute value of y minus 2 is equal to e, and then everything here is the exponent. So x to the 5th over 5 plus the ln of 2. Now, before we continue solving this, it's important to note that when you have these here, when you look at anything raised to an exponent and you have a function that is basically being added, that means that we would have had e raised to the x to the fifth over 5 times e to the ln of 2. Because think about it, if you had x squared times x to the third, that is x to the fifth because it's 2 plus 3. So it's the same scenario here. We have the exponents that were being added, so that means that it must have been e to the x to the fifth over 5 times e to the ln of 2, which is why we would add those exponents. Now the whole reason of doing that is since we have ln as part of my exponent, that means that e raised to the ln of 2 is just 2, since e and ln would cancel. So this, the absolute value of y minus 2, is equal to 2e raised to the x to the fifth over 5. Now we're going to solve for y. But because this is absolute value, we would have to split this into two equations because what is in here could either be positive or negative. So we have y minus 2 is equal to 2e raised to the x to the fifth over 5, or y minus 2 is equal to negative 2e raised to the x to the fifth over 5. Since, like I said, absolute value could be positive or negative. Now we would add the 2 over to both sides of these equations. So y is equal to 2 plus 2e raised to the x to the fifth over 5, or y equals 2 minus 2e raised to the x to the fifth over 5. Now we have to figure out which one of these is it. And what we're going to do is plug in this initial condition and check which one works. So if I plug in 0 into the first equation, we get 0 is equal to 2 plus, and anything raised to 0 is just 1, so this would be 2 times 1, which is 2. Now 0 does not equal to 2 plus 2, so it's not this version. That means that it must be this one. So let's see what happens if we plug it in. We get 0 is equal to 2 minus 2 e raised to the 0 is just 1. 0 does equal to 2 minus 2. Therefore, it is this solution. Okay, let's try another one that's similar to this. We have here dy dx is equal to y minus 1 over x squared. And we have the initial condition of f of 2 is equal to 0. So first we need to separate the variables and make sure that the x's are on the left and the y's are on the right. So I'm going to multiply the dx over. So we have dy is equal to y minus 1 over x squared times dx. And then what I'm going to do here is I'm going to divide this y minus 1 over to the other side. So that way we have all of the y's on the same side. So we have dy over y minus 1 is equal to 1 over x squared dx. Now we can rewrite this 1 over x squared as, here we have the dy y minus 1 is equal to x to the negative 2 dx. Now we can integrate both sides. Now here, remember, the derivative of y minus 1 is dy, which is in the numerator. So this is the ln of the absolute value of y minus 1 is equal. Now I'm going to add 1 to this exponent, so x to the negative 1, and divide by negative 1. So I can rewrite this, oh, and of course the plus c. So I can rewrite this general solution as the ln of the absolute value of y minus 1 is equal to negative, because of this negative 1 over x plus c. So now I'm going to take this initial condition and plug it in, so that way we can solve for c. So y is 0 and 2 is x. So the ln of 0 minus 1, which is negative 1, is equal to negative 1 over 2 plus c. Now the ln of negative 1 of the absolute value of negative 1 is the ln of 1, meaning that the ln of 1, which we know is 0. And this is going to equal to negative 1/2 plus c. So we would have to add the 1/2 over, making c equal to 1/2. So now we're going to come back to my general solution here and plug in c. So we have the ln of the absolute value of y minus 1 is equal to negative 1 over x plus 1 over 2. Now we need to solve for y. So remember, when you have e to cancel it out, when you have ln, you cancel it out using e. So this will cancel, and we have the absolute value of y minus 1 is equal to e raised to the negative 1 over x plus 1 over 2. Now, I don't have to separate this like I did before in this example, where we had a similar situation, but the exponent had the ln. And the reason why I had rewritten it is because I know that e and ln would cancel, so this would make this equation simpler. But in this case here, my exponent does not contain ln, so I don't need to necessarily rewrite that in any other way. So because this is absolute value, that means that we're going to need to separate our equations to get both the positive and the negative version, so we can figure out which one would be the correct answer, since remember, we are looking for the particular solution. So we have either y minus 1 is equal to positive e raised to the negative 1 over x plus 1 over 2, or y minus 1 is equal to negative e raised to the negative 1 over x plus 1 over 2. So to solve for y for each one, we're going to add the 1 over. So y is going to equal to 1 plus e raised to the negative 1 over x plus 1 over 2, or y equals 1 minus e raised to the negative 1 over x plus 1 over 2. So now to figure out which one of these is correct, we are going to plug in that initial condition. So 0 is equal to 1 plus e raised to the negative 1 over 2 plus 1 over 2. So this means that 0 is equal to 1 plus e raised to, this is going to end up being 0, so 1. 0 does not equal to 1 plus 1, so this cannot be my answer. So I'm just going to make sure that this is the correct answer, just in case if something goes wrong, we know that we need to go back. So I'm going to plug in the initial condition. So 0 is equal to 1 minus e raised to the negative 1 over 2 plus 1 over 2. So this gives me 0 is equal to 1 minus, and then e raised to 0 is 1. So this is true. So therefore, my final answer is y equals 1 minus e raised to the negative 1 over x plus 1 over 2. Now let's look at a sample multiple choice question. We have here that the acceleration of a particle moving along the x-axis at time t is given by a of t is equal to 6t minus 2. If the velocity is 25 when t is equal to 3, and the position is 10 when t is equal to 1, then the position x of t is equal to, and we need to solve for that particular equation. So we're going to have to integrate several times. Now we are given that the velocity is 25 when t is equal to 3. So this means that v of 3 is equal to 25. And then we are also told that the position is 10 when t is equal to 1. So that means x of 1 is equal to 10. So now we're ready to start this process. So we have that a of t is equal to 6t minus 2. If I integrate both sides, then that would give me v of t, which is equal to 6t to the third squared over 2 minus 2t plus c. Or we can rewrite that as 3t squared minus 2t plus c. So we have that v of 3 is equal to 25, so we can plug that in. So v of 3 is equal to 3 times 3 squared, which is 9, minus 2 times 3, which is 6, plus c, and this equals to 25. 3 times 9 is 27, minus 6 plus c is equal to 25. 27 minus 6 is 21, plus c is equal to 25. That means that c must equal to 4. So now that we have c, we can plug that in for v of t is going to equal to 3t squared minus 2t plus 4. Now we can integrate one more time to get the position, which is called x of t, which is going to equal to 3t to the third over 3 minus 2t squared over 2 plus 4t plus c. This can be simplified to t cubed minus t squared plus 4t plus c. So we are told that x of 1 is equal to 10. So x of 1 is going to equal to 1 to the third, which is 1, minus 1 squared, which is 1, plus 4 plus c is equal to 10. 1 minus 1 cancels, so we have 4 plus c equals to 10, making c equal to 6. So my equation, this is my general solution there for position. My final equation for x of t is going to equal to t to the third minus t squared plus 4t plus 6, which is c. Now we're going to look at some sample FRQs. We have here, consider the differential equation dy dx is equal to 3x squared over e raised to the 2y. So it says here, find a solution y is equal to f of x to the differential equation satisfying f of 0 is equal to 1/2. So that is my initial condition. So first we would have to separate the variables. I noticed that the x's are diagonally across and so are the y's, so we can just cross multiply what we have here. So we have e raised to the 2y dy is going to equal to 3x squared dx. Integrate both sides. Now here, this is e to the 2y. I noticed that this is a composite function. So when we are integrating, we have to check if the derivative of the inner function is being multiplied by the outer function. So what I have here is that the derivative of 2y would be 2. We're missing the 2 here. So I would have to multiply by 2. But since I'm multiplying by 2 inside of the integral, I have to divide by 2 outside of the integral. So now that I've set that up, we can basically ignore the 2 and just integrate the outer function. And the integral of e is just itself. So this would give me 1/2 e raised to the 2y is equal to 3x to the third over 3 plus c, which can be simplified to 1/2 e to the 2y is equal to x to the third plus c. So now we're told here my initial condition is f of 0 is equal to 1/2. So we can plug in 1/2 for y and 0 for x. So we get 1/2 e raised to the 2 times 1/2, so just 1, so half e is equal to 0 to the third, which is 0, plus c. So c is equal to half of e. So now we can write out our, from our general solution, we can plug in c. So we get 1/2 e raised to the 2y is equal to x to the third, plus c, which is 1/2 e. We want to solve for y, so what we can do here is multiply by 2 to get rid of that 1/2. So we get e raised to the 2y is equal to 2x to the third plus e. Now we can cancel out the the e by applying ln to both sides. So we get 2y is equal to the ln of 2x to the third plus e. And finally, divide the two. So y is going to equal to 1/2 of ln of 2x to the third plus e. And this would be my particular solution that they were asking for. Now for part B, it says to find the domain and range of the function found in part A. Now for our function here, the domain is limited to whatever is inside of ln has to be greater than 0, since ln is not defined for negative numbers, which is why every time that we integrate and we get ln, we use those absolute value bars. So we take whatever is inside of ln, which is 2x to the third plus e, and you make it greater than 0. And now we're going to solve for x to figure out what our domain is. So we subtract the e to both sides, and we get 2x to the third is greater than negative e. Divide the 2. So x to the third is greater than negative e over 2. And then cube root both sides. When you cube root, you are allowed to have a negative inside of that root. So my domain would be for x is greater than the cube root of negative e over 2, which in interval notation, we could write that as the cube root of negative e over 2 to infinity, since that means that it's the right side of that value because it's everything that's greater than that number. Now the range, however, the range is going to be from negative infinity to infinity. And this is because if you look at the ln graph, ln does this. It goes down forever and up forever. So that includes all of the y values. So negative infinity to infinity. Let's look at one more FRQ. We have here that a particle moves along the x-axis so that at any time t is greater than or equal to 0, its acceleration is given by a of t is equal to 6t plus 6. At time t is equal to 0, the velocity of the particle is negative 9, and its position is negative 27. So we have two conditions here. We have that v of 0 is equal to negative 9, and we'll say p of 0 for position is equal to negative 27. So let's start with part A. Find the velocity of the particle at any time. That means that we want to find what the equation is for v of t. So we have that a of t is equal to 6t plus 6. And we have to integrate both sides. And don't forget to close the integral here with the dt. So when we integrate a of t, that is v of t, is equal to 6t squared over 2, which is 3t squared, plus 6t plus c. We have the condition that v of 0 is equal to negative 9. So v of 0, which is negative 9, is going to equal to 3 times 0 squared plus 6 times 0 plus c. This is all 0, so that means that c is equal to negative 9. So my equation for v of t is going to be 3t squared plus 6t minus 9. And that's my answer for A. Now for part B, it says to find the net distance traveled by the particle over the interval 0 to 2. Now net distance is when we integrate v of t. So we're going to do the integral from 0 to 2 of 3t squared plus 6t minus 9 dt. So we integrate this. 3t squared would be 3t to the third over 3, so t to the third, plus 6t squared over 2, which is 3t squared, minus 9t, and we're going to evaluate that from 0 to 2. So we're going to plug in the 2. 2 to the third is 8, plus 2 squared, which is 4, times 3 is 12, minus 9 times 2, which is 18. Minus, now when we plug in the 0, everything would just be 0. So we get here that 8 plus 2 is 20, minus 18 is 2. We are not given any units, but if we were, we would write our units here. But since we're not, this is my net distance, 2. Now it says to find the total distance traveled by the particle over the interval 0 to 2. So in order to find the total distance, we must first check if the particle changes direction. So we need to figure out when v of t is equal to 0 and see if it changes direction, meaning if it changes from positive to negative or negative to positive. So we have our v of t, which is 3t squared plus 6t minus 9, and we're going to make that equal to 0. I can factor out a 3, which will give me t squared plus 2t minus 3 is equal to 0. And then we can factor that to be t plus 3, t minus 1. So we get two critical numbers here. T is equal to negative 3 and 1. But remember that t represents time. So we cannot have this negative 3 as a critical number because there's no such thing as negative time. So we're only going to test t is equal to 1. So I'm going to create my little number line here. I'm going to use my factored version. If I plug in 0, I get a positive times a negative, so negative. And if I plug in 2, I get a positive times a positive, which is positive. So that means that my particle does change direction. So I want to get the total distance, which total distance, as a reminder, is when you integrate from a to b the absolute value of v of t dt. But remember, we don't really know how to integrate this, so a way of bypassing this absolute value is we're going to integrate from 0 to 1, because that's where it changes direction, of v of t, which is the 3t squared plus 6t minus 9. dt. We're going to get the absolute value of that plus the absolute value of the integral from 1 to 2 of 3t squared plus 6t minus 9. Now we had already figured out what this integral was over here, right? The t cubed plus 3t squared minus 9t, but now we're just evaluating for different intervals. So we have the absolute value of I'm just going to separate this here like that. T cubed plus 3t squared minus 9t, and we're evaluating that from 0 to 1, plus t cubed plus 3t squared minus 9t, and we're evaluating that from 1 to 2. Okay, so now we're going to plug all of this in. When we plug in the 1 to the third is just 1, plus 3 times 1. So we have here 1 plus 3 minus 9. And if I plug in 0, everything is just 0. Plus, now here we got to plug in the 2. So we get 2 to the third, which is 8, plus 2 squared is 4, times 3 is 12, minus 18. And now we plug in the 1. So 1 plus 3 minus 9. So 1 plus 3 is 4, minus 9 is negative 5, but it's within the absolute value, so 5. Plus, then here we have 8, this is the 20 minus 18, which is 2, minus 1 plus 3 is 4, minus 9 is negative 5, so minus negative 5 becomes plus 5. So we get 5 plus 7, which is 12. And this would be my total distance. And that's basically it for solving differential equations.